You know, people are always asking me about the laws of physics, what they mean, whether they're really true, whether we can trust them. And I tell them, look, the laws of physics aren't like the laws that some king wrote down and everyone has to follow. They're descriptions. They're our best attempts to describe what nature actually does. And here's the thing that gets me every time, the thing that really makes me stop and think. There's only one rule in science that we never, ever break. Not because we don't want to, but because we can't. It's not a law of nature, it's a law about how we do science itself. And that rule is this: if your theory disagrees with experiment, it's wrong. That's it. Doesn't matter how beautiful your mathematics is, doesn't matter how elegant your equations are, doesn't matter if you're Einstein or Newton or anybody else. If the experiment says no, then you're wrong. Now let me tell you why this is so important, and why it's actually much more interesting than it sounds at first. See, when I was a young guy studying physics, I thought science was about finding the truth. I thought we were going to discover the real laws that govern the universe, the fundamental principles that are actually there, written into the fabric of reality. And in a way, that's what we're doing. But the longer I worked in physics, the more I realized that what we're really doing is something different, something more subtle. We're making models. We're creating mathematical descriptions that let us predict what's going to happen in nature. And the only test we have for whether those models are any good is, do they work? Do they make predictions that match what we actually see when we do an experiment? I remember when I was working on quantum electrodynamics, my theory about how light and matter interact. I spent years developing these techniques, these diagrams that people now call Feynman diagrams, and all these mathematical tricks for calculating what should happen when electrons and photons bounce off each other. And you know what? The mathematics was beautiful. It was elegant. It had this wonderful structure to it. But none of that mattered until we could compare it to experiment. We had to calculate the magnetic moment of the electron, for example, and then see if it matched what the experimenters measured. And when those numbers agreed to something like 10 decimal places, then we knew we were onto something. Not because the theory was beautiful, but because it worked. But here's where it gets really interesting. That same theory, quantum electrodynamics, it has problems. If you push it too far, if you ask it questions about what happens at very high energies or very short distances, it gives you infinity as an answer. Now, that's clearly wrong. Nature doesn't give you infinite answers. So we know the theory is incomplete. We know it's going to break down somewhere. But does that mean we throw it out? No. Because within its domain of applicability, within the range of energies and distances where we can test it, it works perfectly. It makes predictions that agree with experiment to an astonishing degree of precision. This is what I mean when I say the only rule we never break is that experiment is the ultimate judge. We don't demand that our theories be complete. We don't demand that they be philosophically satisfying. We don't even demand that they make sense to our intuition. All we demand is that they agree with what nature actually does. And if they don't, we change the theory. Let me give you another example, one that really drove this home for me. When Einstein developed his theory of general relativity, he replaced Newton's theory of gravity. Now, Newton's theory had been around for over 200 years, and it worked fantastically well. It predicted the motions of the planets, it explained the tides, it let us calculate all sorts of things with incredible accuracy. But there were these tiny discrepancies. The orbit of Mercury, for instance, didn't quite match what Newton's theory predicted. It was a small effect, just 43 seconds of arc per century in the precession of Mercury's perihelion. Most people would have ignored it. They would have said, well, Newton's theory is so good everywhere else, this must be some measurement error, or maybe there's some other planet we haven't discovered yet. But Einstein didn't ignore it. He developed a completely new theory of gravity, one that was mathematically much more complicated, conceptually much more difficult to understand. In his theory, gravity isn't a force at all, it's the curvature of spacetime. Mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. It's a beautiful idea, but it's also weird. It doesn't match our everyday intuition about how things should work. And when Einstein first proposed it, a lot of people were skeptical. But then he made predictions. He said that light from distant stars should be bent when it passes near the sun. He said that clocks should run slower in strong gravitational fields. And most importantly, he calculated the orbit of Mercury, and it came out exactly right. That 43 seconds of arc per century that Newton couldn't explain? General relativity got it perfectly. That's when people started to take the theory seriously. Not because it was elegant, though it is. Not because it made philosophical sense, though in some ways it does. But because it made predictions that agreed with experiment. And here's the crucial point: Newton's theory wasn't wrong, exactly. It's still perfectly good for calculating the motion of planets under most circumstances, for engineering bridges and buildings, for launching rockets. It's an approximation, a special case of the more general theory. But in the domain where we can test it, where the gravitational fields aren't too strong and the speeds aren't too close to the speed of light, it works fine. This brings me to something that I think is really important to understand about how science works. We're not looking for absolute truth. We're looking for better and better approximations. Each new theory should contain the old theory as a special case, a limiting case that applies under certain conditions. And each new theory should make predictions that we can test, predictions that differ from the old theory in ways we can measure. I saw this very clearly when I was working on the Manhattan Project during the war, and then later when I was at Caltech. We were always checking our calculations against reality. We'd calculate how a bomb should behave, or how particles should scatter, and then we'd compare to what actually happened. And whenever there was a discrepancy, we'd go back and figure out what went wrong. Maybe we made a mistake in the calculation. Maybe our model was missing something. Maybe we didn't understand the experiment properly. But we never said, well, the theory is so beautiful that the experiment must be wrong. If the experiment disagreed with the theory had to give way. Now, I want to talk about something that might seem like a contradiction to what I've been saying. Sometimes in physics, we do believe in theories even before we can test all their predictions. We extrapolate. We make guesses about what should happen in situations we can't yet observe. And sometimes we're right. But here's the key: we only do this as a temporary measure, and we always come back to experiment as soon as we can. The theory is a guide, a suggestion about what to look for. But it's not the final word. The final word always comes from nature. Let me tell you about something that bothered me for a long time. In quantum mechanics, we have this principle called the uncertainty principle. Heisenberg discovered it, and it says that you can know both the position and the momentum of a particle with perfect accuracy at the same time. The more precisely you know one, the less precisely you can know the other. Now, when this was first discovered, there was a lot of philosophical debate about what it meant. Did it mean that particles don't have definite positions and momenta? Was it just a limitation of our measuring instruments? Was it something fundamental about the nature of reality? And you know what? Those philosophical questions are interesting, but they're not really physics. The physics is in the mathematical formalism and in the predictions we can test. We can calculate what should happen when we try to measure both position and momentum, and we can compare that to experiment. And what we find is that the uncertainty principle works. It makes correct predictions. Whether particles, really, have definite positions and momenta is a question that might not even be meaningful. What matters is that our theory correctly predicts what we'll measure when we do an experiment. I used to have arguments about this with people who wanted quantum mechanics to be more intuitive, more like classical physics. They'd say things like, surely the electron must be somewhere, even if we don't know where it is. And I'd say, look, the question isn't what you think should be true based on your everyday experience. The question is, what does the mathematical formalism predict, and does that prediction agree with experiment? And if it does, then the formalism is doing its job, regardless of whether it makes sense to our classical intuition. This is hard for people to accept sometimes. We want our theories to match our intuition. We want them to describe a world that makes sense to us. But nature doesn't care what makes sense to us. Nature does what it does, and our job as physicists is to figure out how to describe it, how to predict it, not to make it conform to our preconceptions. I remember giving lectures at Cornell, and later at Caltech, and students would ask me to explain why things work the way they do in quantum mechanics. And I'd tell them, I can't explain why. I can tell you how. I can show you the mathematics, I can show you how to calculate what's going to happen, and I can show you that those calculations agree with experiment. But if you want to know why nature chose to be quantum mechanical rather than classical, I can't help you. Nobody can. That's just how nature is. And this brings me back to the central point. The only rule we never break is that experiment is the judge. We can speculate all we want about why nature works the way it does. We can develop beautiful mathematical theories. We can have deep philosophical insights. But in the end, if our theory doesn't agree with what happens when we actually do an experiment, We have to change the theory or admit that we don't understand. Now, you might think this means that science is always uncertain, always tentative. And in a way, that's true. We're always ready to revise our theories if new experimental evidence comes along. But here's what's amazing. Despite this uncertainty, despite the fact that we're always ready to change our minds, we've built up this incredible edifice of knowledge. We can predict the behavior of atoms with astonishing precision. We can design computers and lasers and nuclear reactors. We can send spacecraft to the outer planets and have them arrive exactly where and when we predicted. All of this works because our theories, even though they're approximate, even though they might be replaced by better theories in the future, are very, very good approximations within their domain of applicability. Let me tell you about something that happened when I was on the commission investigating the Challenger disaster. We were trying to figure out why the space shuttle exploded, and there were all these theories flying around. Some people thought it was one thing, some people thought it was another. And there was a lot of pressure to come to a quick conclusion, to not rock the boat, to go along with what the higher-ups wanted to say. But I kept coming back to the evidence. What did the data actually show? What did the physical debris tell us? And when I did my little demonstration with the O-ring in ice water, showing how the rubber became brittle in cold temperatures, that wasn't because I had some beautiful theory about how O-rings should behave. It was because I looked at the evidence, I thought about what could cause the kind of failure we saw, and I tested it. Simple as that. The O-ring in cold water became stiff and didn't seal properly, just like the O-rings on the shuttle in the cold weather on the morning of the launch. That's science in action. You look at what happened, you form a hypothesis about why it happened, and you test it. If your test confirms the hypothesis, you've probably found something. If it doesn't, you go back and think some more. You don't insist that your theory must be right because it's elegant, or because you thought of it, or because your boss likes it. You follow the evidence. This is why I've always been skeptical of theories that can't be tested. If you tell me you have a theory about the universe but there's no way to test it experimentally, then I'm going to be very suspicious. Maybe it's true, maybe it's not, but if we can't test it, it's not science. It might be mathematics, it might be philosophy, but it's not physics. Physics is about describing the natural world in ways that can be verified by experiment. I remember in the early days of string theory, some people were very excited about it. They said it might be a theory of everything, a way to unify all the forces of nature. And the mathematics was certainly beautiful. But the problem was, and still is to some extent, that it's very hard to test. The energies required to see the effects of strings directly are far beyond anything we can produce in a laboratory. Now, that doesn't mean string theory is wrong. Maybe it's right. But it does mean that until we can figure out a way to test it, we can't really say whether it describes nature or not. It's a mathematical structure, and maybe someday we'll find a way to connect it to experiment, but until then, it's not physics in the way I understand physics. You see, the beauty of the rule that experiment is the ultimate judge is that it keeps us honest. It keeps us from fooling ourselves. And we're very good at fooling ourselves. I've done it many times. You develop a theory, you work on it for months or years, you become attached to it. It starts to seem obviously true. And then you do an experiment, or someone else does, and it doesn't work out the way you expected. And you have a choice. You can either admit that your theory is wrong, or you can try to explain away the experimental result. Maybe the experimenters made a mistake. Maybe there's some effect they didn't account for. And sometimes that's true. Sometimes experiments are wrong. But you have to be very careful. You have to have a good reason to doubt an experiment. You can't just dismiss it because it disagrees with your theory. I learned this lesson early on when I was working on the Manhattan Project. We'd do calculations, and then the experimenters would measure things, and sometimes our calculations didn't match. And we'd go over the calculations again, looking for errors, and we'd talk to the experimenters about their procedures. And sometimes we found errors in our calculations, and sometimes the experimenters found errors in their measurements. But the point is, we took the discrepancies seriously. We didn't just wave them away. This attitude, this commitment to experimental verification, is what makes science different from other ways of knowing. In mathematics, you can prove things with absolute certainty, but you're working within a defined system of axioms and rules. You're not necessarily describing the physical world. In philosophy or theology, you can argue about ideas, but there's no final arbiter, no way to definitively settle a dispute. But in science, we have experiments. We have nature itself as the judge. And nature can't be fooled. You can fool yourself, you can fool other people, but you can't fool nature. I think this is one of the most important things young physicists need to learn. Don't fall in love with your theories. Don't get so attached to an idea that you can't let it go when the evidence goes against it. Be willing to be wrong. In fact, expect to be wrong most of the time. That's how science works. You try things, most of them don't work out, and occasionally you stumble onto something that does work, something that agrees with experiment. And then you build on that. When I was developing quantum electrodynamics, I tried lots of different approaches. Most of them didn't work. I'd calculate something, and it would give nonsense, or it wouldn't agree with what we knew about how electrons and photons behave. And I'd throw those approaches away and try something else. I wasn't precious about it. I wasn't saying, well, this approach is so clever that nature ought to work this way. I was saying, does this approach give me answers that match reality? If yes, keep going. If no, try something else. And you know what's interesting? Different people developed quantum electrodynamics in different ways. Schwinger did it one way, very formal and mathematical. Tomonaga did it another way. I did it with my diagrams and path integrals. And in the end, we showed that all these different approaches were equivalent. They all gave the same predictions. And those predictions agreed with experiment. That's what mattered. Not which approach was more elegant or more intuitive, but that they all made the same testable predictions, and those predictions were correct. This is another important point about science. There can be multiple ways of looking at the same thing, multiple formulations of the same theory. As long as they make the same predictions, as long as they agree with experiment, they're all equally valid from a scientific standpoint. You might prefer one over another because it's easier to calculate with, or because it gives you better intuition about what's going on, but nature doesn't care which formulation you use. Nature just does what it does. I've sometimes been asked whether I think we'll ever have a final theory of physics, a complete description of nature that we'll never need to revise. And my answer is, I don't know. Maybe we will, maybe we won't. But here's the thing, even if we do find such a theory, we'll only know it's the final theory if it keeps agreeing with every experiment we can think of to do. We'll never be able to prove that it's final in some absolute sense. We'll only be able to say that we haven't found anything it can't explain yet. And that's okay. That's the nature of science. We're always building on what came before. Newton built on Galileo. Einstein built on Newton. Quantum mechanics built on classical mechanics. Each new theory doesn't completely overturn what came before. It extends it, generalizes it, shows where the old theory was an approximation and what a better approximation looks like. I think some people find this unsatisfying. They want certainty. They want to know the truth with a capital T. But that's not what science gives you. Science gives you the best description we currently have, subject to revision if new evidence comes along. And that's actually more valuable than absolute certainty, because it means we're always learning, always improving our understanding. Let me tell you something else that I think is important. When I say that experiment is the ultimate judge, I don't mean that theory doesn't matter. Theory matters enormously. Good theory guides us in designing experiments. It tells us what to look for, what questions to ask. It organizes our knowledge and helps us see connections between different phenomena. But theory is always the servant of experiment, not the master. Theory proposes, experiment disposes. I spent a lot of my career doing theoretical physics, working out calculations, developing new mathematical techniques. And I loved it. There's a real joy in figuring out how to calculate something that nobody's been able to calculate before. But I always kept in mind that the point of the calculation was to make a prediction that could be tested. If I couldn't figure out a way to test it, either directly or indirectly, then I'd wonder whether I was really doing physics or just playing with mathematics. And sometimes experiments surprise us. Sometimes nature does something we didn't expect at all. That's when things get really exciting. Because then we have to figure out what's going on. We have to revise our theories or come up with new ones. This has happened many times in the history of physics. The discovery of radioactivity was a surprise. The discovery of the electron was a surprise. The discovery that the universe is expanding was a surprise. Each of these discoveries forced us to rethink our theories, to develop new frameworks for understanding nature. And the beautiful thing is, we could do that. We could modify our theories to account for the new phenomena. Because our theories weren't dogmas. They weren't articles of faith. They were working descriptions of nature, and when nature showed us something new, we updated our descriptions. This is why I've never understood people who are afraid of science, who think it's too cold or too rigid. Science is actually incredibly flexible. It's just not arbitrary. We can change our theories, but we have to change them in response to evidence, not just because we feel like it. That's the discipline of science, and it's what makes science reliable. I remember when I was young, reading about the history of physics, and I was struck by how many times the experts were wrong. People believed in the ether, the medium that light was supposed to travel through. That turned out not to exist. People believed that heat was a fluid called caloric. That turned out to be wrong too. People believed all sorts of things that we now know are false. But here's the key: we know they're false because we did experiments. We didn't just decide we didn't like those theories. We tested them, and they failed the tests. And that gives me confidence. Because even though we're probably wrong about some things today, even though future physicists will look back and shake their heads at some of our ideas, we have a method for correcting those errors. We have the rule that experiment is the ultimate judge. As long as we stick to that rule, as long as we keep testing our ideas against reality, we'll keep making progress. You know, sometimes people ask me if I believe in this or that theory. And I tell them, belief is the wrong word. I don't believe in quantum mechanics the way I might believe in a religion or a political philosophy. I accept quantum mechanics because it works. It makes predictions that agree with experiment. If tomorrow someone did an experiment that contradicted quantum mechanics in a fundamental way, I'd be fascinated. I'd want to understand what was going on. Maybe we need to modify quantum mechanics, or maybe we need to replace it with something else. I'd be surprised, certainly, because quantum mechanics has been tested so thoroughly. But I wouldn't cling to it just because I believe in it. This is the attitude I've tried to cultivate in myself and to teach to my students. Be skeptical. Question everything. But be fair. Follow the evidence wherever it leads. Don't dismiss ideas just because they're new or strange, but don't accept them just because they're fashionable or because important people believe them. Test them. See if they work. That's the only criterion that matters. And here's something that I think is really wonderful about this approach: it's democratic. It doesn't matter who you are, where you're from, what your background is. If you can do an experiment that shows something, that evidence speaks for itself. Nature doesn't care about your credentials or your connections. Nature is the same for everyone. Of course, in practice, science is done by people, and people have all sorts of biases and prejudices and political considerations. Sometimes good ideas get ignored because they come from the wrong person or the wrong place. Sometimes bad ideas get promoted because they're popular or because they serve someone's interests. But in the long run, as long as we keep doing experiments, as long as we keep testing our ideas against reality, the truth has a way of coming out. Because you can suppress an idea, you can ignore evidence for a while, but you can't change what nature actually does. I've seen this happen. I've seen theories that were very popular fall by the wayside because they didn't agree with experiment. I've seen other theories that seemed crazy at first gain acceptance because the evidence supported them. The process isn't always smooth, it isn't always fast, but it works. It works because we have this one unbreakable rule: if your theory disagrees with experiment, it's wrong. So when people ask me what the most important principle in science is, this is what I tell them. Not any particular law of physics, not any specific theory or equation. But this methodological principle: experiment is the ultimate judge. Everything else in science follows from that. Our theories, our models, our mathematical frameworks, they're all tools for understanding and predicting what experiments will show. And if they fail at that task, we change them. This might seem obvious, but it's actually quite profound. It means that we can never be completely certain about anything in physics. There's always the possibility that the next experiment will surprise us, will show us something we didn't expect. But it also means that we can be confident in the theories we have, to the extent that they've been tested and confirmed. We're not just making things up. We're describing reality, or at least, we're making models that successfully predict what reality will do. And that, to me, is the beauty of physics. We're uncovering the patterns in nature, the regularities, the rules that govern how things behave. And we're doing it in a way that's self-correcting, that gets better over time, that builds on what came before while always remaining open to new discoveries. All because we follow this one simple rule: if it doesn't agree with experiment, it's wrong. That's the only rule science never breaks, and it's the rule that makes everything else possible.